Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So hi everyone. It's a great pleasure to welcome Jeff Rauenhorst, who is a VP of Business Development in a Bay Area startup called Perforated Controls. And they've been doing some interesting work in controlling data center environmental conditions using sensor networks, data based on sensor networks. And today he's here to talk about the projects they're doing and some of the results that they got. Welcome.
Okay, thank you. And I want to try to make this as interactive as possible today. So hopefully you guys can get something out of this and learn something a little bit about what we're doing. So since we're a small group, maybe do you want to quickly go around and introduce yourself and maybe what you want to get out of today, just so I have a little idea of what you guys are interested in?
Sure. I'm Lori. You talked to my
Hello, Lori.
one of the data centers that deployed some of the temperature and humidity sensors
Great,
down at
great.
Tech 2.
Nice to meet you.
Just kind of seeing how everything's tying together.
Sure. Great.
This is Bo. I'm Porto Lori.
Okay, great.
I'm Garrett.
Garrett,
I work on the DC Genome project with G.
Okay, perfect.
I'm Victoria Pansini. I'm actually the IT Microsoft wireless architect for all of our Wi-Fi stuff on campus.
Okay.
And I'm interested in seeing if you're using Wi-Fi or Zigbee or some other type of technology, and how, if you've done both of those, if you tie those together.
Okay, yeah, we'll talk about that. Absolutely.
I'm on the cloud computing future team in Microsoft Research. Just looking in similar areas as this.
Okay, great.
And I'm Dave O'Hara, and I'm a vendor, but I work a lot of green initiatives.
Okay. Vendor with whom?
I have my own company.
Ah, great. Okay. Okay, and I think there might be some people online. Welcome. So, yeah, again, my name is Jeff Rauenhorst with Perforated Controls. Just for a little background on myself, I have a chemical engineering degree, and I worked for Honeywell in their process control group for several years, implementing IT systems to run large pharma and biotech companies. So I kind of have a very IT-centric background. I have an MBA from the UC Berkeley School of Business, and joined Perforated Controls last summer. So Perforated Controls, just a little background, is a company that's focused on energy management and saving our customers energy. We were started in 2004, really focused on the building market, specifically older buildings. And our founder, Cliff Federspiel, came out of UC Berkeley, where they had been doing a lot of research into wireless sensor networks, and where a lot of the core wireless sensor network technology came out of. So he really adapted their technology out of the university and brought it to the commercial building market. Our founder also has a PhD from MIT in the intersection between artificial intelligence and HVAC controls. So he has a very unique background, which is kind of appropriate for what we're doing. We've been in both the building and data center market for a while. Hopefully today I can kind of tell you a little bit about what we're doing around using wireless sensor network data to drive environmental control specifically within data centers. So feel free to stop me if you have any questions. Hopefully we can make this pretty interactive. Some of these slides, I mean, we kind of all know some of the problems in data centers. First, server manufacturers and ASHRAE specify that we should measure the inlet air going into servers, but very few people do it. Microsoft is clearly in the lead in its deployment of actually measuring inlet air temperatures. The controls piece too, even if you're measuring the inlet air, typically your control system isn't controlled with inlet air. It's usually controlled by return air coming back to the crack units in the data center, or by supply air. But both ways of controlling really don't have any idea of what's going on with your actual servers. So there's clearly a lot of inefficiency and hotspots and other thermal issues that crop up. So it takes a large deployment to really understand your thermal environment, but then when you actually begin to approach the control problem of what's happening in data centers, it's a very difficult problem. First of all, as you know, data centers tend to be open plan, so they're quite large open areas. There's not the areas of influence are quite wide, so one cooling unit can affect a lot of different units. It's very hard to divide up, or as they call zone, a data center to control temperatures. So there's a big challenge with this kind of open plan control. When you build your HVAC systems in data centers, you want them redundant. If one unit fails, you don't want your whole data center to go down. But with that redundancy comes a lot of complexity. How do you, if you have redundant units, how do you use them appropriately? When do you use them? And there are some big challenges too with fighting. I mean, hopefully you guys don't have in your data center, but I've walked into some where we see two units literally 4 feet away from each other, and one's humidifying, the other's dehumidifying. We've seen some heating, which they should never do in any data center. So the coordination of cooling in data centers is a huge problem, and it's not very well done from what we've seen in a lot of data centers, and hopefully Microsoft is ahead of the curve. You guys are fortunate enough to have a lot of PhDs on staff, and they probably are helping you with your data center cooling control. Not everybody is that lucky, and it's very hard to have one full time. So, as we say, we like to we package a PhD and put it in a box. So around some intelligent cooling control. So there's big problems on both the measuring side and also the control side in data centers. And what we've seen is, surprisingly, data center cooling control typically is worse than, say, a building like this. They monitor the rooms and have a pretty good understanding of how the rooms work, but in data centers, the control paradigm is quite weak. So this is what we do. So we have, I forgot to, I left it out in the car, but we have our own wireless sensor modules, and we'll talk a little bit more detail of exactly what they are. This is what they look like. Our model is that we actually run 2 thermistors straight off them. We put this on the top of a rack and run it down to measure the top and bottom of a rack. That really provides us the insight into the thermal environment in the data center. What we do with that then is a bunch of analysis to really understand, the simple things like, excuse me, where are your hot spots, and where are some of the issues. But really, that data allows us to, as you've probably seen, CFD modeling or computational fluid dynamics modeling kind of has a picture of the airflow within a data center. We're able to take all our data from our sensor network and build a statistical CFD model basically in our software that is dynamic and changes depending on your environment. You take out a couple racks, you put in a couple racks, or even during the day as somebody, server farm serving up videos, gets really active when all the high school kids come home. We can dynamically model that. And then what allows us to do is actually begin to control your cooling units and coordinate them to match your cooling capacity with your IT load. The salesy thing is we typically can show an ROI of less than 2 years. So, how do we do this? Well, you can see a very ugly rack of one of our customers. Hopefully yours all look much better. But we typically put our module at the top, running thermistors down. You guys have a little different way of doing it, which is fine. This is deployed across. We're just measuring inlet air going into servers, and usually deployed every kind of 4 to 5 racks, but depending on the particular customer site. So we deploy these, and this collects our data. This technology is a wireless mesh networking technology. So it's the simplest way is to say it's Zigbee-like. Again, I think the next slide will go into a little bit more of the details. So there's a mesh network that is formed, and pretty pictures, and but the key thing is all this data then we use to feed into basically this intelligent algorithm that dynamically controls cooling.
So what is your data yield
Sorry?
What's the data yield on that wireless network?
Data
Yield. How much data you get? Do you get
Oh.
all the samples you need, or
Yeah.
occasionally got job packets? And
So that's a good question. The technology is based on, if you were to dust networks, we use dust network radios.
okay.
So they make their mesh networking radio. It's aligned with the wireless HART standard, so it's not Zigbee. They are incredibly robust. Their main customers use them in places like oil refineries and heavy industry. We get close, like 99.9 or something of that level of reliability of packets. It's a time synchronized protocol, so it's not collision based. So we get very good reliability of our data. Is that? Yeah.
What's your sampling frequency, or does that?
It's typically a minute to 2 minutes. It's configurable, but yeah, usually our customers are doing a minute to 2 minutes. Yeah.
What do you interface with? Do you interface with like an Ethernet backend or another wireless network, or?
I didn't put that in there. So our wireless sensors talk to a gateway, which is then plugged into Ethernet. Yeah. So a typical gateway can support about 256 or 255 sensors.
And what frequency are you using?
It's the 900 megahertz on licensed spectrum. Yep.
The algorithm that controls the temperature, how far back does it take of samples? Does it just take the most recent readings from temperature sensors to determine what the next temperature should be? Or?
Right. So I think the simple answer is, well, kind of both. It uses historical data to build up a model and does things like perturb a system, right? Turn down a crack unit just a little bit and see how the whole system responds to develop its internal model. So it's using a lot of the history data to determine, basically, to be able to answer questions like, if this rack gets hot, which cooling unit should I turn up and down? But then it's also using real-time data to see how that model adjusts over time. This is supposed to be a picture of a wireless mesh network, but you guys, I think, probably all know how that works. So a little bit more on the technology piece. It is all battery powered. The dust radios are incredibly power efficient, so we get 3 to 10 years of battery life, and we can monitor that battery life and show you how many months left you have on the batteries. So time synchronized protocol. There's about 3 layers of security. So it's a kind of a pseudo-random frequency hopping, which is kind of a security measure in itself. It's got encryption and keys and a couple other security features built into it. We found it's incredibly robust and reliable, both in data centers as well as, we deploy these in a lot of buildings with concrete and rebar, which tend to be very tough RF environments. So it works very well.
Cordless phones doesn't interfere with it.
And it's smart enough that if it does hit a channel of interference, it'll just stop using that. So again, very robust. Yep.
So how much time does it take for you to transfer the data back to your backend, and based on this data, make a decision? How does this time affect your control decisions?
So it's a good question. I don't know the exact answer, but I think it's less than a minute or two. So if we're getting a sample rate of, say, a minute, to get it back to the controls, it might be a couple seconds. And then usually within a minute, it should make a control decision based on that.
What is the largest network you put in, like with a single base station? How many wireless nodes?
So it can support 255. I think we typically are a little conservative. So we typically put in like maybe 170 at a time. It actually supports longer battery life because you have less nodes that are both routing and sending signals. But yeah, so we've done 170 pretty easily. Let's see. As far as, Dust Networks is our supplier. We're not a wireless sensor company. We don't make firmware or program. If you really want to learn more about the technology, Dust Networks, they've been a great partner to work with and pretty robust technology. So our solution is entirely web-based. So from an architecture perspective, you deploy wireless temperature sensors. It talks to a base station, which then via Ethernet is connected to a server that runs our control algorithms. And that server then can control crack units directly. We have a wireless control module as well that has, actually, the picture. Yeah. So it actually has outputs. So we can directly plug into variable frequency drives on the control units, or on the cooling units, or chilled water valves, or both, to directly control the units. And a lot of our customers have pretty basic data centers, and the cooling units are standalone, so we can directly control them. So we do both the sensing and the control piece wirelessly.
So your control module is also wireless?
Yep, yeah, it's wireless. It has a 0 to 10 volt output, so it can talk to just about anything.
And the battery also lasts for 3 years?
Yeah, so if we have a 0 to 10 volt, if you have 2 AA's, it's only 3 volts. Yeah. So we have to power that. But typically, if you're plugging into variable frequency drive, it has power right there. So most devices you talk 0 to 10 volts to has power. So we just pull it from there. Batteries act as a backup. The other piece that we do is there's building management systems, BMSs, or building automation systems in your data centers. So we can speak and communicate with those systems. So BACnet is an open protocol that's used to communicate to building management systems. We can communicate to BMSs and then control set points and cooling units through that. Typically, more sophisticated customers already have their cooling units networked together, and then we just pass through their system so they can use the same interface. They can do manual overrides of our control if they desire. So, and then we also do analog integration. We can plug directly into a control panel and send them an analog signal. So we can also do web services, XML interfaces, ODBC interfaces. Our system really can bridge the gap between IT and facilities, which is kind of a challenge in this space. Yeah, so if you're from a facility side, our software is kind of like a supervisory control. So we sit on top of your existing control and do energy efficiency. Have you guys looked at demand response at all in your data centers? Demand response, are you familiar with that? During the hottest days in the summer, you turn down your energy usage and get paid by the local utilities instead of turning.
We have one of our power companies.
Okay.
Not all of them.
Right. So our software enables some of the demand response capabilities too, for both buildings and data centers. So, come on, there we go. You asked a question about the control technology. I mean, here's a little bit, high level on a slide, but I can talk to it a little bit more. The system is really designed to solve a very difficult problem. When you deploy sensor networks, you get hundreds and thousands or tens of thousands, or probably even more in your case, data points within a data center, and you get lots of data. But say in a 50,000 square foot data center, you'll probably have about 40 cooling units, roughly. So you have this problem where you have thousands of points controlling a few points, 30, 40, 50 points. So that's a very difficult control problem, and that's basically what we have solved. And we can handle lots of points. We're waiting for the day when servers with their internal temperature probes actually finally get to communicate out to the rest of the world. I'm not sure if you guys have looked at that, but most server manufacturers have a temperature probe, usually somewhere between 4 to 6 inches inside the intake into a server. And so there's some interfaces, like a company called Richard Zeta has an interface. Intel has their IPMI interface. Once we can pull out that data, we'll have even more temperature readings. But our algorithm kind of does some advanced control to really understand, how all these points really can drive, 30 or 40 points. And that's what we've solved. And it's intelligent in the sense that it actually learns. It has, a lot of artificial intelligence built into it, and it can adapt. I think a big challenge in, a lot of colo facilities we've talked to is customers take racks in and out, and the load is actually quite dynamic, both from the number of servers and also the output of the servers, right? Because, data center server just typically doesn't always, run at 80% utilization all the time. We would love it if that was the case, but load really shifts over the course of the day, and we've seen our system, for one particular customer at 7:30 in the morning, the whole data center basically wakes up with the rest of the company. So it can dynamically respond to that. And then it really has the ability to determine which cooling unit, which craw or crack, influences which server, and how that changes over time. And if you've been in data centers, with under air floors, there's cabling and all sorts of stuff underneath that can change over time. You run a bunch of network cables, and so the environment changes, and it's very tough to model, from a point in time. So our system kind of dynamically corrects for those type of things.
Could you talk a little more? I don't want to get into things you don't have to.
Right.
What AI models did you use, or is it?
Yeah, so that's probably about all I can say right now. All of this technology is patent pending that we're developing, and that's kind of our secret sauce.
Do you guys look at just proactive, or just reactively control the temperature? So if you see temperature increasing, you increase the cooling, or do you actually try to proactively predict what will happen in the future?
Right. No, that's a great question. Right now, it is reactive, and we've developed this core control model that works. But clearly, in the future, we are going to develop a more reactive and predictive capability, and especially as we begin to have more customers interested in demand response. If we can tell it's going to be at an incredibly hot day today, we can do some pre-cooling, or depending on your HVAC system, but and make sure the data center is cool. A couple minutes before all the servers typically go up at 7:30, or some backup algorithm runs at 3 o'clock in the morning on a regular basis. So we're not there yet, but it's definitely a direction we're heading. I won't talk to this much because I'm sure you've had the same experience, that deploying these sensor networks adds a lot of value to begin to see where there are issues in your data center, and gives you an insight for your facilities people that they've never had before. And there's a huge value in that, and we talk to our customers and say we recommend that first. Coupled with our system, we can get energy savings right away, but then you can really look at some of the other best practices out there, especially around cooling, whether it's hot aisle or cold aisle containment, making sure all your holes are plugged in your under air floor distribution, blanking, all this stuff. Having a system in that gives you a lot of data is really a good first step, and it sounds like you guys are doing this. So then it really, why we like this wireless sensor module approach is that we call kind of our service we provide persistent commissioning, but it allows customers to really can make sure your data center is always running optimally, over time. And we know that. I've seen data centers that are put up and they're working perfect on day one, and then day 100 they're already kind of out of whack. So you really get real-time feedback on what's happening. This is kind of an interesting insight. I'm not sure if you guys have run into this, but this is always kind of fascinating. So a lot of racks have doors on them, right? And they're 95% perforated, and most people say, oh, that's fine, and there's lots of studies saying it doesn't affect airflow. But we've seen, this is one instance where there was over a 10-degree drop by just opening the front and back doors. And we were actually working in a customer's cloud cluster. They had about 4 rows of 15 racks of brand new servers running a cloud instance. All new gear. I think it was IBM. Both equipment and racks, and their doors were brand new. There was a 19-degree temperature difference inside, where the inlet, where the air is going into the server, when the door was open and closed. And this was, fully loaded. They're blanking panels. It's kind of everything that you'd expect. But I think what we think is that the door provides just enough back pressure that any of these little holes can get the hot air flowing backwards, coming from the outlet, just because that a little bit of back pressure makes it easier for the air to come to the front instead of going out the back. So you've probably seen results like this deploying your systems, but we see that's a big benefit. And so our little side campaign is take off your doors. And of course, more important than me talking, here's a couple case studies for customers of what we've been able to achieve with our system. So this is the State of California Franchise Tax Board, which their data center is quite busy right now because all their tax filings go through there. So this was a pilot project for us that we did with Lawrence Berkeley National Lab. And so they're right now verifying all our numbers and making sure they're accurate. So this was a small data center, 10,000 square feet, with 12 Liebert chilled water cooling units. They had built it out about 60% and then virtualized it. And so they brought it down to about 40% capacity. But what was interesting is their cooling units were all on all the time. Their operators had tried to turn off a couple, but kept on getting hot spots. So they were never comfortable trying to turn it down. We put in, it was only, so it was 25 wireless sensor modules measuring 50 points. So, not a very data dense deployment, but, it was sufficient. We typically, implement it on the outside of the rows, just where typically are the hottest temperatures. We installed variable frequency drives on 4 of the 12 cooling units. Typically, they were the ones closest to the racks. And we did some rearrangement of tiles and reset some of the set points of the cooling units. And what our implementation is controlling these 4 VFDs, and then the remaining 8 we would turn on and off as necessary.
Let me try to understand. So you control the fan speed.
Yep.
And then you manually set the set point of the chill water or the air return temperature? What do you mean the set point?
Right. So each implementation is slightly different. In this particular one, they were Liebert VFDs, so they have this retrofit kit. So we were sending commands to the Liebert units through their SiteLink Gateway protocol, which were resetting the set points, so basically for return air, because they were controlling off return air.
So you didn't touch that loop. So there's still a return air.
Right.
And chill water valve opening control.
Yeah. So the local Liebert unit in this case actually controlled the VFD speed and the chilled water valve according to its own controls. But we were changing their set point, so that was the feedback loop we used for that system. Okay. Other instances, we have basically made the Liebert units kind of dumb cooling coils where we actually control the VFD and the chilled water valve independently. Again, it's just depending on the customer. And then for the other 8 units, we turn them on and off because they only had 1 speed, and as well as adjusting their set points to adjust their chilled water valve position. So what was interesting is at any given time, typically 6 to 8 of the units were turned off by our system. And which ones were turned off kind of depended on the conditions of the servers, while, of course, maintaining all the temperatures within ASHRAE limits. I think what was interesting is where you get some kind of counterintuitive behavior that we didn't even expect is that most of the servers were clustered on kind of one side of their data center. And what happened is the VFDs were next to those servers, so they were typically on but at a lower speed. The cooling units in the middle of the data center were off, but there was typically one that was furthest away from the servers that was on, which seemed very counterintuitive at first. Kind of our analysis seems to imply that it was basically providing back pressure. So all the cool air coming from the cooling units next to the servers stayed there, and this just provided some back pressure. And which crack unit was on or off varied over time based on load. So that's kind of the behavior you get with some of this dynamic cooling control. With a 10,000 square foot data center, we were still able to get some pretty significant energy savings, primarily from fan savings, but also from some chilled water savings.
So intuitively, if you have some workload in the data center, you want to put it, concentrate it into a small number of servers, or you want to spread it across many servers to make the cooling unit most efficient?
That's an interesting question. I'm not sure if I'm qualified to fully answer that, but I think one of the things that we've seen, and the next case study will kind of show it, is that if you have a more heavily loaded data center, it's actually better to keep all your units on but turn them down to say like 80% than have 80% of them on at full blast and 20% off.
We looked at installing the VFDs in our crack units at one point, but we were at 80-85% capacity.
Okay.
So they were running all the time anyway, so it
Yeah.
didn't make any sense to try and have that variable speed. We wouldn't get any cost saves because we had to run them all the time anyway.
At full,
so, yeah.
right. And
I mean, they might have been at 80%. I'm just saying that we weren't able to take advantage of turning some of them off at the current time.
Yeah, what's interesting is, so if you turn down a VFD 80%, you get turn it down 20%, you get about 50% energy savings because there's a cube law relationship between the fan speed and power. So by turning down all your crack units 80%, you'll get more energy savings than turning off 20% of them.
Yeah, I don't have the VFDs installed. So.
Yeah. So in heavily loaded data centers, there are, there's a little less bang for your buck, but I think where the opportunity is using
well,
your.
You said that the data centers are dynamic, so things change.
Right.
They went from probably full servers now to virtual, so that
Yep.
changed the dynamics.
Yep.
And I'm seeing that now at our data center as we're
Right.
decommissioning the older we get rid of the old equipment.
Right.
Bring in more, so it's interesting to think about it.
Yeah, and in heavily loaded data centers, there's still an opportunity for VFDs, because if you're able to use your wireless sensor network to control, hopefully, you'll slightly lower your cooling required, and then you can load up your data center more, and you get higher densities, safely. So there's still an opportunity to get some excess capacity out of your existing facilities with this type of infrastructure. You can see this is when we turned it on. This is they had a bunch of alarms based on relative humidity, and if you raise your temperature, your relative humidity goes down. So they had to turn on their humidifiers for a little while to get their relative humidity back up, which is kind of an interesting story of how much energy humidification actually uses. Yeah.
Maybe I didn't understand G's question, but I have a similar one.
Sure.
So in the case where you have a data center, and let's say, half your machines are heavily loaded, and half of them are running pretty much at idle. Is it best to have the heavily loaded computers very condensed and try to cool just those, or spread the heavy load across a wide number of, or spread the heavily loaded machines across your physical data center so you have more space in between the heavily loaded?
Right. So again, I'm not the expert, but if you had variable frequency drives installed, it would probably make sense to spread that load across your data center. And then your risk of hotspots is also decreased. If you don't, it might make sense to, where there is excess cooling capacity, put your load and kind of do a little bit more of matching of IT load physically with your cooling load. Yeah, so 58% fan reduction. This is over 13% of your total IT, or your total data center energy usage. You start getting some big numbers. Yeah.
In this first graph we just saw the energy savings from changing the fan speeds and everything else, right? Do you have any data on how you affect the temperature distribution? Because this is based on what you're basing your control decision, right? You're getting a step with the temperature distribution, you're trying to enforce a better one, and this is how you get these energy savings. So do you get a really much better and even distribution in terms of temperature?
Right, so that's a good question. I don't exactly know. I know that we've been able to, in all these instances, get these energy savings while making sure the temperature readings we're getting were within ASHRAE limits. So I should have that information. That would be good to know, and I'm sure someone from our team can run that analysis. Here's another data center. Again, it's quite small. This was, for a large software company in the Bay Area that they wanted kind of a pilot to see how our system works. So again, kind of small. I think what's interesting is that, so it's 5,000 square feet, 6 CRAWs, so chilled water Liebert units. But our implementation was slightly different. We installed 6 VFDs, and we directly controlled the VFDs. They didn't have a building management system or anything, so we were actually controlling them directly. And again, pretty small. But we deployed measuring 48 temperature points. They had gone through an audit with a local engineering firm of all the different best practices they could roll out. Their data center, it was about half hot aisle, cold aisle. It was kind of a mess. It was kind of a lab facility. They had a bunch of holes in their floor. They could have done containment. Done a hot air return plenum in the ceiling. But they chose to do nothing of that and implemented our system first, just to kind of see. And so all this stuff goes in quickly. So what was interesting is the energy savings they were able to achieve were equal to what they predicted with all of the various energy efficiency measures if they were implemented. So, basically, their data center had a lot more cooling than it was needed, so we were able to turn down the fans to about 50% most of the time. So we get about 80% fan energy savings, and pretty large energy savings. It was interesting. I was in there when they turned it on, and it's amazing how quiet the data center got. Because the fans in the units and even the UPS units, the buzz of them went down a little bit as the IT load went down. So this is again where we were directly controlling chilled water valve position and fan speed. So that's kind of an overview of what we do. I wasn't sure exactly how this would work, but you'd be curious to hear a little bit of feedback now that you've kind of heard a little bit of what we're doing more on the control side. How would this fit into your deployment of wireless sensors? Have you started, I think last time we talked in the fall, you were mainly doing data collection and analysis. If you begin to look at the control piece, where do you stand with your wireless sensor network project? Yeah, it's a question for anyone out here. Yeah, anyone.
We started looking at the control piece. We built a test chamber in the largest data center. We were a little bit sort of constrained on later on what we were doing on that, moving power party and some other stuff. But this is definitely interesting. That's something is naturally fit into the next step once we have that data. We're just facing a little bit more challenge right now, more pressing in terms of being able to archive and store that data for long-term use.
Okay.
So that's why we move our focus, I told you, a little bit more into the data compression and data storage part. But this control stuff is definitely one of the interesting points. And as I said, we want to take a joint computing and physical control approach. That sort of leads to the question, right? If your workload changes, how do you consolidate the workload that can make your facility side or cooling side life easier? And how can you dynamically control the cooling side to adapt to those kind of workload changes? So we're investigating things like virtual machine migrations and load balancing, shut down machines and those things. Add the cooling factor into that to make that decision. That's where we're going.
Yep. Yeah, we're talking with a client too about pulling a lot more data, both IT data as well as as I mentioned, the server temperature data, and how do you actually do control based on utilization of your CPU in the server, and some of those features. I think we'd all love to be there. The challenge is for a lot of customers, for IT and facilities are still kind of two different worlds. So yeah, it sounds like the data, the amount of data you're collecting has been kind of a unexpected gotcha that you've kind of figured out. Any other challenges or any kind of big insights that you guys have seen from your experience? It's gone as expected?
Can't tell you.
Yeah. Fair enough. Okay. Okay. Yeah, this is, sales guy threw this in. But yeah, so hopefully that gave you a little bit of idea. I mean, we're using wireless mesh networking technology. It's kind of off the shelf, but I think the real step forward we've taken is with the control piece and having the dynamic control. I think the interesting part is this really works well with other best practices out there. For example, hot aisle or cold aisle containment. We've done that with some clients, and they're able to get some great results. Because as you contain your environments, the responses and the changes in those environments become a little bit more critical. So having the good sensing data in there adds a lot of value to your control strategy. So, and as I'm sure you've seen, the installation of these wireless sensors is pretty non-obtrusive to the operations of the facility. So that's about all I have. If you guys have any more questions or...
So, as you work in this industry, where do you see the next big challenge? Is it just, we have the wonderful solution and everybody just use it? Or some challenge and technical challenge in particular?
Yeah. So, of course, we'd love to have everybody out there with data centers use our solution, because we're all in business to make money. But I think we've touched on two really large challenges here. I mean, the predictive control that you mentioned. You can begin to, especially owner occupied data centers, so like Microsoft's or Yahoo's or IBM's or some of those type of people, where they have kind of a standard, a little bit more predictability in their IT load. Being able to do some predictive control. It's a little harder in colo facilities, but still applicable. I think that probably the more pressing challenge is merging this world of IT and facilities, getting CPU utilization data, getting hard drive utilization data, and pulling that all in to the facilities people, getting them to talk. So you can provide, you guys have, I know Microsoft has done a good job at some of the dashboards around data center utilization. Most customers aren't there. You guys are definitely on the forefront of that to really to get the IT and facilities people seeing the same information, making decisions off the same information, as well as then driving the control piece of it too. We would love to get to the point where, the facilities control can talk to your VM installations and coordinate, where VM instances run, both physically within a data center or between data centers, based on the going power rate in an area or capacity. I think there's some big opportunities there. But all those challenges really go down to how do facilities and IT people work together. And it becomes a little bit of a cultural thing within companies of how you align these two organizations so that they work together. Yeah. And the other big piece is that a lot of data centers out there are very old. I think over half the data centers are over 5 years old in the US. And so how do you retrofit your existing data centers? Because building a new data center is easily $1,000 a square foot to build out. So we see the financial challenges, at least in the short term, are quite large for a lot of our customers. So, yeah.
One just detail that maybe you said this, but with the data that you collect, do you store most of it for long-term use, or? Because I mean, I know you said for right now, or at least the two examples you gave are kind of smaller.
Right. Yeah, we're not running to the amount of
And is it just that right now you're just running on smaller data centers, or do you do something with that data, either get rid of it or?
Right. So, and this is my assumption, is that we don't have as sensor-rich of an environment as your deployments here. My guess is you put a lot more sensors. Are you doing like a sensor per rack? I'm not sure what level of data you're collecting, but we don't collect quite as much data to do the control within the data center. So given hard drive capacities, we don't see a big problem in the foreseeable future, with installations even up to 100, 200,000 square feet. So I think the simple answer is we haven't hit that issue at this point. But what we typically see long term is that a lot more of the data around fan energy is a little bit more pertinent to keep over the long term, especially as customers trend their energy usage. Some of the temperature data, probably can be compressed into 15 or 20-minute intervals over time, for anything that's over a couple of years old.
So is it up to the customer?
At this point, yeah. But at this point, we save all the data and don't run into capacity issues at this point.
So are there any gotchas in your deployment?
So I think one of the interesting pieces is that where you actually position the sensors is pretty important. I'm not sure if you've run into this, but
much denser. So.
Yeah, but even across one rack, typical volume server, the temperature between the sides and the middle and the side, there can be a 4 to 5 degree temperature difference. So, it's interesting as we begin to work with more customers, that positioning of the sensors is important. As I've talked about with the doors, by putting on the outside of the door versus inside the door, we've seen up to 19 degree temperature differences. So that's kind of a gotcha, is that you need to be a little bit careful of exactly where you place the sensor on a rack. What other piece? Oh, we've had some data centers where we have these variable frequency drives that people will go around and turn them up, and just as they're walking through the data center in some like an R&D facility for a large customer that we have. There's just a guy who likes to turn them up because he wants to make sure his server is cool. So, there's some cultural things too around when you walk into a data center, most people, you've seen the, heavy coats sitting right outside and they want their data center cold. And, I know like Christian Bellotti is a big proponent of running your data centers as hot as possible. So I think some of the gotchas around understanding the culture of the data center and the users and your customer.
So when you do control, right, you're turning fans up and down and setting the chill water loss. What kind of transitors? Do you see a big spike when you turn something off and then it gradually settle, or the spike smooth? Do you worry about the sort of the short-term big changes in terms of temperatures?
Yeah, no, it's a good question. I know the system can adapt, and also, just like any control mechanism, there are some tuning parameters of how quickly the system responds. It has some PID loops built in if you guys are control engineers. So a little bit of it kind of depends on the particular customer. So some of that is configurable.
For every facility?
We have a pretty good set of kind of base parameters, but one of the we as a company offer a service to do a bunch of analysis on their data on, say, a monthly basis that we can recommend some fine tuning and making sure your system runs as well as possible. So yeah, we have done some minor adjustments with the control piece. Specifically when the system turns on, yeah, typically we see a drop in fan speed. Some customers, it's pretty constant. Typically we'll see daily fluctuations. Like I said, one customer, 7:30, it'll be running at its minimum at 50%, and then it'll start fluctuating between 50 and 60% over the day, and then go down at the end of the day, just based on usage. Just to jump back to one of the challenges that I just remembered is, so there's fans in all these computers, right? Most of them now are variable speed. And I think what challenge for all of us is that we can control, the cooling units, but if we ramp up the temperatures too high, then the fans on these servers will kick on, and they're incredibly inefficient because they're really small. So they can actually negate a lot of the energy usage that you might be saving in your larger units. This example of a 15-degree difference in the door, you'd open up the door and you'd hear the fans in the servers ramp down. So I think a challenge, again, as we can pull more information out of the IT systems, is making sure we look at a holistic perspective of cooling, both from your cracks as well as your fans and your servers. So I think that's another interesting part. Yeah?
So on the examples that you gave, it seemed like the sensors weren't very dense, like you didn't put them in there very dense.
Mm-hmm.
But you talked about getting the temperature sensors from the motherboards and whatnot,
mm-hmm.
which obviously would be orders of magnitude
Yes.
more dense.
Yes.
So do you think you'll be able to use that data efficiently and actually get it further improvements from additional data? Or is there some kind of point where getting more data won't actually help you become, it's more data, but it's not going to help.
Right. So it's a great question. What's interesting is the way we've built our software, we can support as much data as you can get, and we will try to extract the most information. I think implementations will really tell if there's that much more information to learn from the data coming out of servers.
So was there a reason why you picked the particular density you did on those examples, or I guess do you have some intuition where that data doesn't help you enough to justify additional sensors?
Right. So to be frank, the decision around number of sensors is as much a control as an economic decision. The sensors cost money, and there's a certain point of each customer has a certain budget. So we have some intuition about placing the sensors with an appropriate density to really understand the thermodynamic environment of your data center, as well as the density to make sure your costs stay low and get an appropriate return. With taking temperatures from servers, your marginal cost of an additional temperature point is incredibly small, and so we think we can get a lot more value out of that. The number of points I think will actually be necessary too, because what we've seen is the temperature probes in the servers are pretty cheap and relatively inaccurate. So from a statistical perspective, if a rack is 42U, and if you have 42 servers in there, you can do some statistical analysis around the law of large numbers. If you have over 30 points roughly, you'll be able to get a better estimate of what the temperatures are. So when you go to measuring server temperatures, having that data will be important, because a lot of that will be filtered out anyway because of bad sensors or rogue points.
Do you think you'll move away from wireless sensors, or will you use them in conjunction?
I think the simple answer is time will tell. We'll always have a system to be able to do it both ways. We've had a couple clients, particular telcos, that won't do wireless in their data centers, especially anything with a 911 switch. They don't even allow you with cell phones in there. So there are some environments that tend to, that won't do wireless. So there are also some points that are hard to monitor. So we actually typically put a sensor on the crack units to measure return and supply error because the sensors in these Liebert units are notoriously poor. So a wireless sensor there is the only way to get better accurate data. So I'm sure it'll probably be a heterogeneous environment, at least in the short term. Yeah.
All right.
Good.
Thank you, Jeff.
Yep.